Absolute value functions. Until the 1920s, the so-called spiral nebula were believed to be clouds of dust and gas in our own galaxy, some tens of thousands of light years away. Then astronomer Edwin Hubble proved that these objects are galaxies in their own right. At distances of millions of light years, today, astronomers can detect galaxies that are billions of light years away. Distances in the universe can be measured in all directions. As such, it is useful to consider distance as an absolute value function. In this section, we will continue our investigation of absolute value functions. Understanding absolute value. Recall that in its basic form, f of x equals absolute value of x, the absolute value function is one of our toolkit functions. The absolute value function is commonly thought of as providing the distance the number is from 0 on a number line. Algebraically, for whatever the input value is, the output is the value without regard to sign. Knowing this, we can use absolute value functions to solve some kinds of real-world problems. Absolute value function. The absolute value function can be defined as a piecewise function. F of x equals the absolute value x equals piecewise x if x is greater than or equal to 0, negative x if x is less than 0. Graphing an absolute value function. The most significant feature of the absolute value graph is the corner point at which the graph changes directions. This point is shown at the origin in Figure 2. Figure 3 shows the graph of y equals 2 multiplied by absolute value of x minus 3 plus 4. The graph of y equals absolute value x has been shifted right 3 units, vertically stretched by a factor of 2, and shifted up 4 units. This means that the corner point is located at 3, 4 for this transformed function. Q&A. If we couldn't observe the stretch of the function from the graphs, could we algebraically determine it? Yes. If we are unable to determine the stretch based on the width of the graph, we can solve for the stretch factor by putting in a known pair of values for x and f of x. Q&A. Do the graphs of absolute value functions always intersect the vertical axis, the horizontal axis? Yes. They always intersect the vertical axis. The graph of an absolute value function will intersect the vertical axis when the input is 0. No. They do not always intersect the horizontal axis. The graph may or may not intersect the horizontal axis depending on how the graph has been shifted and reflected. It is possible for the absolute value function to intersect the horizontal axis at 0, 1, or 2 points. See Figure 7. Solving an absolute value equation. In other types of equations, we touched on the concepts of absolute value equations. Now that we understand a little more about their graphs, we can take another look at these types of equations. Now that we can graph an absolute value function, we will learn how to solve an absolute value equation. To solve an equation such as 8 equals the absolute value of 2 minus x, we must notice that the absolute value will be equal to 8 if the quantity inside the absolute value is 8 or negative 8. This leads to 2 different equations we could solve independently. Knowing how to solve problems involving absolute value functions is useful. For example, we may need to identify numbers or points on a line that are at a specified distance from a given reference point. An absolute value equation is an equation in which the unknown variable appears in absolute value bars. For example, the absolute value of x equals 4, the absolute value of 2x minus 1 equals 3, the absolute value of 5x plus 2 minus 4 equals 9. Solutions to absolute value equations. For real numbers a and b, an equation of the form absolute value a equals b with b greater than or equal to 0 will have solutions when a equals b or a equals negative b. If b is less than 0, the equation absolute value of a is equal to b has no solution. How to. Given the formula for an absolute value function, find the horizontal intercepts of its graph. 1. Isolate the absolute value term. 2. Use absolute value a equals b to write a equals b or negative a equals b, assuming b is greater than 0. And 3. Solve for x. Q&A. Should we always expect two answers when solving the absolute value of a equals b? No, we may find one, two, or even no answers. For example, there is no solution to 2 plus the absolute value of 3x minus 5 equals 1. Access these online resources for additional instruction and practice with absolute value. Graphing absolute value functions. Graphing absolute value functions 2. OpenStacksCollege.org. Inverse functions. A reversible heat pump is a climate control system that is an air conditioner and a heater in a single device, operated in one direction. It pumps heat out of a house to provide cooling. Operating in reverse, it pumps heat into the building from the heat outside. Even in cool weather, to provide heating as a heater, a heat pump is several times more efficient than conventional electrical resistance heating. If some physical machines can run in two directions, we might ask whether some of the machines we have been studying can also run backwards. Figure 1 provides a visual representation of this equation. In this section, we will consider the reverse nature of functions. Verifying that two functions are inverse functions. Suppose a fashion designer traveling to Milan for a fashion show wants to know what the temperature will be. He is not familiar with the Celsius scale. To get an idea of how temperature measurements are related, he asks his assistant, Betty, to convert 75 degrees Fahrenheit to degrees Celsius. She finds the formula C equals 5/9 multiplied by F minus 32, and substitutes 75 for F to calculate. 5/9 multiplied by 75 minus 32 is approximately 24 degrees Celsius. Knowing that a comfortable 75 degrees Fahrenheit is about 24 degrees Celsius, he sends his assistant the week's weather forecast from Figure 2 for Milan, and asks her to convert all of the temperatures to degrees Fahrenheit. At first, Betty considers using the formula she has already found to complete the conversions. After all, she knows her algebra and can easily solve the equation for F after substituting a value for C. For example, to convert 26 degrees Celsius, she could write 26 equals 5/9 multiplied by F minus 32. After considering this option for a moment, however, she realizes that solving the equation for each of the temperatures will be awfully tedious. She realizes that since evaluation is easier than solving it, it would be much more convenient to have a different formula, one that takes the Celsius temperature and outputs the Fahrenheit temperature. The formula for which Betty is searching corresponds to the idea of an inverse function, which is a function for which the input of the original function becomes the output of the inverse function, and the output of the original function becomes the input of the inverse function. Given a function f of x, we represent its inverse as the inverse function of x, read as f inverse of x. The raised -1 is part of the notation. It is not an exponent. It does not imply a power of -1. In other words, f inverse of x does not mean 1 over f of x, because 1 over f of x is the reciprocal of f and not the inverse. The exponent-like notation comes from an analogy between function composition and multiplication, just as a raised to the -1 power, a equals 1. 1 is the identity element for multiplication for any non-zero number a, so f inverse of x, composed of f, equals the identity function that is F inverse composed of f of x equals f inverse of f of x equals f inverse of y equals x. This holds for all x in the domain of f. Informally, this means that inverse functions undo each other. However, just as 0 does not have a reciprocal, some functions do not have inverses. Given a function f of x, we can verify whether sum of the function g of x is the inverse of f of x by checking whether either g of f of x equals x or f of g of x equals x is true. We can test whichever equation is more convenient to work with because they are logically equivalent. That is, if one is true, then so is the other. For example, y equals 4x equals and y equals 1/4 x are inverse functions. F inverse composed of f of x equals f inverse of 4x equals 1/4 multiplied by 4x equals x. And f composed of f inverse of x equals f of 1/4 x equals 4 multiplied by 1/4 x equals x. A few coordinate pairs from the graph of the function y equals 4x are -2, -8, 0, 0, and 2, 8. A few coordinate pairs from the graph of the function y equals 1/4 x are -8, -2, 0, 0, and 8, 2. If we interchange the input and output of each coordinate pair of a function, the interchanged coordinate pairs would appear on the graph of the inverse function. Inverse function. For any one-to-one function, f of x equals y, a function f inverse of x is an inverse function of f if f inverse of y equals x. This can also be written as f inverse of f of x equals x for all x in the domain of f. It also follows that f of f inverse of x equals x for all x in the domain of f inverse if f inverse is the inverse of f. The notation f inverse is read f inverse. Like any other function, we can use any variable name as the input for f inverse. So we will often write f inverse of x, which we read as f inverse of x. Keep in mind that f inverse of x does not equal 1 over f of x, and not all functions have inverses. How to. Given two functions, f of x and g of x, test whether the functions are inverses of each other. 1. Determine whether f of g of x equals x or g of f of x equals x. 2. If either statement is true, then both are true, and g equals f inverse and f equals g inverse. If either statement is false, then both are false, and g does not equal f inverse and f does not equal g inverse. Finding domain and range of inverse functions. The outputs of the function f are the inputs to f inverse, so the range of f is also the domain of f inverse. Likewise, because the inputs to f are the outputs of f inverse, the domain of f is the range of f inverse. We can visualize the situation as in figure 3. When a function has no inverse function, it is possible to create a new function where that new function on a limited domain does have an inverse function. For example, the inverse of f of x equals the square root x is f inverse of x equals x squared, because a square undoes a square root. But the square is only the inverse of the square root on the domain bounded 0 to infinity unbounded, since that is the range of f of x equals the square root of x. We can look at this problem from the other side, starting with the square toolkit quadratic function f of x equals x squared. If we want to construct an inverse to this function, we can run into a problem, because for every given output of the quadratic function, there are two corresponding inputs, except when the input is 0. For example, the output 9 from the quadratic function corresponds to the inputs 3 and -3, but an output from a function is an input to its inverse. If this inverse input corresponds to more than one inverse output of the original function, then the inverse is not a function at all. To put it differently, the quadratic function is not a one-to-one function. It fails the horizontal line test, so it does not have an inverse function. In order for a function to have an inverse, it must be a one-to-one function. In many cases, if a function is not one-to-one, we can still restrict the function to a part of its domain on which it is one-to-one. For example, we can make a restricted version of the square function f of x equals x squared with its range limited to bounded 0 to infinity unbounded, which is a one-to-one function. It passes the horizontal line test, and which has an inverse, the square root function. If f of x equals x minus 1 squared on bounded 1 to infinity unbounded, then the inverse function is f inverse of x equals the square root of x plus 1. The domain of f equals the range of f inverse equals bounded 1 to infinity unbounded, and the domain of f inverse equals the range of f equals bounded 0 to infinity unbounded. Q&A. Is it possible for a function to have more than one inverse? No. If two supposedly different functions, say g and h, both meet the definition of being inverses of another function f, then you can prove that g equals h. We have just seen that some functions only have inverses if we restrict the domain of the original function. In these cases, there may be more than one way to restrict the domain, leading to different inverses. However, on any one domain, the original function still has only one unique inverse. Domain and range of inverse functions. The range of a function f of x is the domain of the inverse function f inverse of x. The domain of f of x is the range of f inverse x. How to? Given a function, find the domain and range of its inverse. 1. If the function is one-to-one, write the range of the original function as the domain of the inverse, and write the domain of the original function as the range of the inverse. 2. If the domain of the original function needs to be restricted to make it one-to-one, then this restricted domain becomes the range of the inverse function. Finding and evaluating inverse functions. So once we have a one-to-one function, we can evaluate its inverse at specific inverse function inputs or construct a complete representation of the inverse function in many cases. Inverting tabular functions. Suppose we want to find the inverse of a function represented in table form. Remember that the domain of a function is the range of the inverse, and the range of the function is the domain of the inverse. So we need to interchange the domain and range. Each row or column of inputs becomes the row or column of outputs for the inverse function. And similarly, each row or column of outputs becomes the row or column of inputs for the inverse function. Evaluating the inverse of a function. Given a graph of the original function, we saw in functions and function notation that the domain of a function can be read by observing the horizontal extent of its graph. We find the domain of the inverse function by observing the vertical extent of the graph of the original function, because this corresponds to the horizontal extent of the inverse function. Similarly, we find the range of the inverse function by observing the horizontal extent of the graph of the original function, as this is the vertical extent of the inverse function. If we want to evaluate an inverse function, we find its input within its domain, which is all or part of the vertical axis of the original function's graph. How to? Given the graph of a function, evaluate its inverse at specific points. 1. Find the desired input on the y-axis of the given graph. 2. Read the inverse function's output from the x-axis of the given graph. Finding inverses of functions represented by formulas. Sometimes we will need to know an inverse function for all elements of its domains, not just a few. If the original function is given as a formula, for example, y as function of x, we can often find the inverse function by solving to obtain x as a function of y. Finding inverse functions and their graphs. It says, now that we can find the inverse of a function, we will explore the graphs of functions and their inverses. Let us return to the quadratic function f of x equals x squared, restrict it to the domain bounded 0 to infinity unbounded, on which this function is 1-to-1 and graph it as in figure 7. Figure 7. Quadratic function with domain restricted to bounded 0 to infinity unbounded.